Assalamualaikum.
Waalaikumsalam. Halo.
Prof. Prof, apa kabar, Prof?
Ya, kerja.
Ya, Prof.
Ya.
Saya join nama M Abdullah ni sebab saya tak boleh tukar nama.
Oh ya.
Saya cuba tukar nama tak boleh tadi.
Oh ya.
Ya, Prof Ratna.
Halo, Assalamualaikum.
Assalamualaikum warahmatullahi
Apa kabar?
Ya, alhamdulillah.
Gimana kabar COVID di sana?
Ya, makin berkurang, alhamdulillah makin berkurang. Tapi masih
sudah open kah? Perguruan tinggi sudah open belum?
Sudah open. Baru semester kami baru semester lah. Oke. Ibu sehat ya?
Sehat.
Ya, alhamdulillah. Nanti bantu ambil gambar gitu, Prof. Retno.
Siap. Saya Pak cari gambar saya biar kelihatan bagus. Backlight.
Saya jangan pakai Zoom jalan backgroundnya. Bentar ya.
Kamu minta nomor Nancy.
Enggak, saya kan tanya, kemarin itu sudah dititipkan ke saya sebenarnya, Prof. Tapi saya enggak berani megang, soalnya uangnya gede. Terus saya baru ingat kan, jenengan bilang, oh iya Mbak, yang itu boleh tak ambilkan, tak Mbak? Iya. Oh itu loh sudah, aku ngomong Profesnya lupa. Siapa?
Ini karena nggak pernah ketemu dia.
Gimana, Pak Menteri sudah datang?
Ya, datangnya esok.
Oh, so.
Cuma kami kena buat preparation. Macam-macam lah. Kena bersihkan lah, kena macam-macam kena.
Ya.
Dia datang mengejut.
Ya.
Datang mengejut. Kami pun last minute prepare everything.
Mana-mana pejabat macam itulah. Ini partisipannya dari kelas Bachelor Photonics dengan Master.
Okay.
Actually almost same. Medical Photonics.
Medical Photonics.
Subject, ya.
By research, Master by research ataupun mixed mode?
By research.
Research.
Sorry. By course.
By
course. Okay.
Master Biomedical Engineering.
Okay.
Dokter Munzir.
Ya.
Nanti habis UTS mungkin sekitar bulan Mei itu juga dengan mata kuliah ini juga ya, satu kali lagi ya.
Insya Allah boleh. Dia 2 kali kan? 2 kali. Insya Allah boleh. Dia 2 kali kan?
Iya.
Insya Allah. Insya Allah boleh. Topiknya berbeza kot?
Iya. Sudah pernah jalan dengan surface plasma resonance?
Pernah juga.
Nah itu aja sampaikan ya. Materi setelah UTS. Pesan sekarang ya diterapkan. Boleh?
Boleh insya Allah boleh.
Ya oke.
Boleh mula ke? Macam mana? Saya dah bersedia ni kalau.
Sekejap. Nanti.
Gimana vaksinnya, Prof Yasin?
Ya, Kak, ngantuk, sleepy.
Iya ngantuk memang.
Sudah vaksin, Muzir?
Belum.
Sudah kali kedua ini.
Oh, boleh ya? Kami masih kena register.
Oh ya.
register tu nak dapatkan schedule untuk vaksin belum dapat lagi.
Vaksin yang mana?
Yang
DECOTA atau Sinovac?
saya pun tak pasti.
Kalau AstraZeneca ini efeknya dahsyat.
Oh ya kah? Yang Prof kena tu apa? Astra
Saya,
punya.
saya Sinovac, tapi di sini ada
Sinovac.
yang AstraZeneca, itu ada yang demam, menggigil.
Oh, side effect dia kuat.
Iya. Kalau Sinovac ini sleepy aja.
Oh.
Ini ada partisipan from UITM mungkin.
Oh.
UITM Terengganu, Dr. Wati pernah dengar? Wati yang student Prof. Sulaiman.
Oh, okay.
Dia kan staff UITM Terengganu.
Halo, Assalamualaikum.
Halo, Dr. Wati.
Saya
Masih ingat Dr. Munjir?
Di open anunya kameranya.
open. Malu.
Sekejap aja lah, sekejap.
Oke tak?
Oke. Kalau nggak gitu Kak Pak Sua. Bila nak main Indonesia nih, Surabaya.
Betul.
Kalau sudah open nanti ya, kalau sudah open bandara belum open ya, penerbangan internasional itu.
Belum. Di Indonesia belum.
Kangen nasi biryani. Nasi biryani kambing kangen ini saya. Aduh, enak banget itu ya.
Tapi yang Johor atau
yang kemarin sama Prof Hamzah itu di mana Prof Yasin?
KL kok.
KL.
KL ya.
Aduh, banyak banget menunya itu, aduh.
Ini udah berapa?
Dr. Munzir dulu ex-student Prof. Sulaiman ke? Pernah jadi?
Prof Nuria di IGM.
Oh, oke. Di Johor
Di Johor lah. Tapi waktu saya buat PhD tu Prof Yasin dia buat visiting professor di IGM.
Oh.
Di situ lah.
Maksudnya PhD di UTM lah?
IGM.
Ya.
Oke.
Tahun berapa kok nggak ketemu saya ya?
Tahun 2015.
Oh, iya.
Baru lagi.
2015.
Kalau saya sekitar 2007 dengan Prof Nuria juga.
Ya.
Ya.
Dengan Maisarah
Ya.
Maisarah. Saya lambat sikit, saya baru sikit.
Ya.
Mana NDIAC-nya? Still working?
No.
Tak working kot. Lama, sistem lama.
Iya.
Petrofizik lah.
Iya. Kalau dekat USM apa? Laser yang
kami tak ada laser sangat. Kami on semiconductor material lah. Tak fokus more on laser lah. Bidang yang berbeza.
Iya. Sekejap, ini Rahman yang apa? Present itu mana Rahman? Daftar hadirnya ini. Sekejap.
Apa dimulai aja Prof Yasin sambil lalu jalan itu.
Iya, nanti ya. Prof aja moderator.
Soalnya nanti habis ini di jalan, buka tok saya nggak apa-apa ya.
Tidak apa-apa. Kan yang dua kuliah ini, dua subjek. Monggo aja langsung nanti saya.
And English, okay?
Mix apa? Mix.
Dr. Mundir and English and Nanu mix.
Mix. Okay,
Yeah.
mix. Okay.
Yeah.
I think
Assalamualaikum. Yeah.
more on English word, English lah.
Ya, PPT in English ya, oke.
Ya.
Ya. Mas Zul, untuk rekaman recording sudah siap ya? Mas Zul?
Sudah record kok Ibu.
Oke. Ya.
Yang itu presensi Mas Yul, tolong Rohman di kontak.
Sudah, nanti aja
Sudah. Ya.
Sudah. Ya. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good evening for all participants in the DECOTA lecture. Today we will hear from Dr. Mundir Abdullah for the DECOTA lecture, with the topic is Introduction to Integrated Photonics. Maybe about 2 hours we will hear about his presentation, and so we will discuss about the material, and maybe for the next collaboration with the University Sains Malaysia for the next collaboration, especially in research and for joint international publication. Okay, for the Dr. Mundir, thank you very much for attending this lecture. And so I see about the Dr. Wati, Zulzilawati. So our student with the biophotonic lecturer and medical photonic for the master degree. Thank you very much for your attending this presentation, and please don't forget, for you all, you must make the about the rangkuman for this lecture, and maybe you can submit this aula. Yeah, maybe Prof. Yafir can discuss again in the next lecture about this material. Thank you very much for all participants, and please, for you, Dr. Mundir.
Okay.
I'm for you. Thank you very much.
Terima kasih. Thank you very much, Prof. Ratna and Prof. Yasin. I will share my screen now. Can you see my screen now? The one that I'm sharing?
Yes.
PowerPoint. All right. Okay. I will start now. Okay. So, Assalamualaikum warahmatullahi wabarakatuh, and good afternoon. Good afternoon to all of the participants in this kuliah DECOTA lecture at Universitas Airlangga. First of all, I would like to thank the organizer, especially the Dean of Faculty of Science and Technology, my good old friend, Prof. Yasin, and Prof. Ratna, for inviting me to give this, to deliver this lecture. Okay, the title of the lecture is going to be on the integrated photonics, but I don't want to make it too specific, because of the wide variation in the audience background maybe. So my lecture will be on the introduction of integrated photonics. By the way, can you hear my voice? Is it clear? Clear, right?
Clear, sir.
I hope
Clear, sir.
it is clear. Okay. So before we proceed, I would like to little bit introduce myself. My name is Munzir bin Abdullah from Institute of Optoelectronics Research and Technology, INO. And I have two affiliations in USM, currently in University of Science Malaysia. The first, my main affiliation is Institute of Optoelectronics Research and Technology, INO. We are actually one of the research institute in USM. Okay, so we focus more on optoelectronics research related to the material science, also the technology that we can use beyond the fundamental. So we can use it as application. And my second affiliation is School of Physics. So both of them are located in the universities in the main campus in USM, University of Science Malaysia. And for those who don't know, USM is located in the Peninsula of Malaysia. We are located in the northern part of Peninsula Malaysia, and our campus is in the Pulau Pinang. It's in Penang Island, basically. So that's a little bit about myself. My background is physics, but I believe being a physicist doesn't preclude us, or does not allow. Doesn't prevent us to do something useful for application, for device, and so on. So we're going to see what the topic that I'm going to prepare, that I have prepared today. What is the application? What's the basic of the integrated photonics, and how we can use it as application later on. So this is the outline of my lecture. The first, I will talk about the transition from the optics to photonics. So what's the difference between the two? There might be a debate on the definition of optics and photonics. The concept of optics and photonics might be debatable, but we look at one of view on this. Next, we will discuss about what is integrated photonics, the idea behind the integrated photonics. We also will talk about the optical system evolution, how the optical system evolved over time. The basic component is in integrated photonics. Next, we will discuss about the basic concept of waveguide. And last but not least is we will...
Hello, Dr. Mudir.
Yes? Dengar tak?
Ya, dengar.
Dengar ya?
Dengar. Ya,
Ya,
clear.
kalau tak dengar saya... Dengar ya?
Dengar.
Okay.
Dengar.
Okay, so last but not least, I will talk about the application of integrated photonics. Just a few emerging application related to integrated photonics. All right. So first, we have the term optics and we have the term photonics. So what is the difference between the two? What is optics? Optics is the science of light. Actually, so optics is one of the pure topics or pure area in physics that study the science of light. So anything related to light, the science behind it can be considered as optics. And optics is the part of science. All right, we can say that optics is part of science. But photonics can be understood as the technology by using optics. All right, so science evolved based on curiosity. This part of light study is called optics, and the technology of using light for the various applications for various devices is called photonics. But this definition might not be agreeable for all of the researchers in the field or expert in the field. Some say that optics is actually the study of light, seeing through or seeing as light as a wave. All right, we know light can behave like a wave, and light also can behave like a particle. So optics, one of the view is optics is the study of light based on its wave properties, while photonics, based on the name photon, it is a study of light application, viewing light as a particle. So, but that might be a different definition there. But first, we will look at the evolution of the optics field. So, optics field. Let me move the. Okay. So, optics field, based on the science of light, can be explained in different theories. Okay, so first we have ray optics. Ray optics is the first theory, we can say it's a theory of understanding the light. So ray optics is the theory to understand light, to represent light as a straight line, as a linear straight line. And these ray optics are able to explain refraction, reflection, but fail in other phenomena. So this is the classical description of light by using ray optics. Okay, so next the theory evolved into scalar wave optics. This is given by Huygens, based on Huygens postulates that light is a wave. All right, it's a scalar wave. So therefore, it creates a new theory of light, which we name it as a scalar wave optics. And now the theory, or the scalar wave optics theory, can able to explain interference, dispersion, and so on, because now we take into consideration the wave properties of light. All right, so this is the second stage. And over the years, the theory emerged because of the optics optical physicists. They are studying what light actually is. So in the end, we have this electromagnetic wave theory, which can be explained by using Maxwell equation. So before that, the physicists don't really know what light really is. So EM wave theory provides the explanation on what light actually is, and it is based on this EM wave theory. Light is actually consists of a propagation of wave, electric and magnetic field, oscillation of electric and magnetic field in the perpendicular or orthogonal direction, and the wave propagates in the direction that is perpendicular to the two. All right, so that's the electromagnetic wave theory. And recently, we need to start looking at the quantum mechanics of photon, because photon is a quantum particles. And to understand this photon physics, all right, involving single photon physics, now we don't talk about light anymore. We talk about a particle called photon. So therefore, since photon is very, very small, is in the quantum realm, we need to use quantum optics or quantum mechanics for that. So that is the evolution of the optics field, or optics field. Like I mentioned just now, optics is the science of light, to study the science of light. So this is actually the baseline, or the main things that can explain the science of light. And if you notice here, each stage is the limit of the previous stage. For example, the scalar wave is actually the limit of what ray optics can explain. Same goes with the EM wave theory. EM wave theory is a limit as what scalar wave can explain. So therefore, we have this backward compatibility. That means quantum optics should be able to explain all phenomena that can be explained by using EM wave theory, scalar wave optics, and also ray optics. I hear some noises. Can you all hear me? Any?
Yes.
I just want to make, okay,
Yes.
right?
Yeah, okay.
All right. So we have this backward compatibility. That means the newer theory can explain what the phenomena that can be explained by previous theory. So that's how the optics evolve. So far it is more on the light itself, right? We study about the lights, not really focus on the application. All right. So there are three main revolutions in optics which enable photonics. Okay, optics is a science of light, I mentioned it just now, and photonics is how we use the light, how we use optics for various applications. So the three main revolution is, the first is the invention of laser by Theodor Neumann in 1960. Okay, so this is actually a first laser made by using ruby crystal as the gain medium. Sorry. Ruby as an active medium, and this is actually the first demonstration of a huge intensity of pencil-like beam with high spatial temporal coherence, which is not observed before the creation of the laser. And if we check the history, the laser has been predicted a few years back by Albert Einstein, the laser phenomena, but it needs few years until Theodore Maiman managed to build laser based on the Ruby as an active medium. All right. So this is actually the laser beam is actually very interesting because we can have a huge energy intensity inside a very small location. We can have huge intensity of light energy in a very confined location. Okay, so that's the first revolution. The second revolution is on the development of semiconductor optical devices. This is based on this is the base of what we have: laser diode, we have the LED, and so on right now. So this is the basic of that. So before the development of semiconductor optical devices, the laser and lighting technology didn't use solid state material, but rather use different kind of excitation. For example, the Nd:YAG laser, they use flash lamp, okay, to excite the Nd:YAG crystal so that it can produce laser. So that is using the crystal as a active medium. But the semiconductor optical devices, when they start to be developed, we can have a much compact laser, which is now we call it laser diode. Okay, so all this is actually enabled by the development of the various semiconductor material into optical devices, and it is actually much more efficient and compact compared to the bulk laser. So in the, like mentioned before, the previous laser uses huge system, so they need to have a flash lamp, they need to have cooling and so on. For example, the most of the laser that time they use gas sensor. That means they need to have a chamber for that gas to reside. And another is they use dye laser, which is a liquid base. So that cannot be miniaturized. That system, bulk system, still can be considered as a bulk. So to achieve miniaturization, we need to have everything inside a chip. So therefore, this is what we have achieved using a semiconductor technology. The third revolution is actually the fabrication technique to produce fiber optics. So nowadays, fiber optics can be produced with a very cheap cost, and we managed to have a very low propagation loss. The signal inside the fiber optics can be traveled, can be transferred, can propagate inside the optical fiber hundreds of kilometers without a minimal loss. So this is the three main revolution in optics, which extend the field of optics, not just study of light. We can also use light into for different application. Okay, and I forgot to mention about the laser. Once when laser has been invented in 1960, actually laser can be regarded as a solution in searching for a problem. That means that time we have laser, and laser can act as a solution, and we can solve any problem by using laser. So that's the keyword when referring to the first laser. Laser is the solution in searching for problem. We have problem, we can solve it by using laser. So that is about the what enables photonics. And actually, it's not just related to that. We have a lot more field in optics actually that pushes photonics, optics and related field towards photonics. The first is electro-optics. Electro-optics is the modulation of light, how we control light by using electro-optical properties, electro-optical material. All right, so basically we have a material and we apply current to it. We apply a electrical signal to it. What happens is the refractive index will change, right? So the basic behind it is when you put more current, we put current flowing into that material, we have more charge carrier, can be electron, can be holes, right? So we have more charge carrier inside the material, and the refractive index of that material will slightly change. All right. So by changing how the current or the current that we injected into the material, we can slightly change the refractive index. So that is the electro-optics. Second is acousto-optics. We modulate, or we change the properties of light by using acousto-optics. So acousto-optics is sound, right? Acoustic. Ultrasonic is acoustic. We can use surface acoustic wave to induce change in our light. So we have light coming in inside the material, and in that material we have these acoustic devices, transducer, and based on the interaction between the surface wave, surface acoustic wave, and in the coming light, we can have a different properties of the output, light output. And another field is quantum optoelectronics. Okay, optoelectronics is the study of semiconductor that can be used for optics application. And since these now it evolved into, or it have combined into a nanotechnology field, so therefore we need to view optoelectronics from the quantum point of view, so give birth into the quantum optoelectronics. Applied disciplines, optoelectronics, optical communication, imaging and display system, optical computing, optical sensing, nanotechnology, and material sciences. So this is what pushes optics towards photonics, which is more on the application side. All right. So what is integrated photonics? This is our topic today, which is the introduction to integrated photonics. So now we'll talk, or we'll discuss what is integrated photonics. The term integrated photonics, the term integrated optics first proposed in 1960 by Miller to emphasize the similarity between the planar optical circuit technology and the well-established integrated microelectronic circuit. So, like I mentioned just now, the word optics and photonics can be used interchangeably. Some people have different definition from the others. Some say that optics and photonics are basically the same thing, but this is up to this is actually can be accepted. It actually consists of a almost same field. All right, so we have the second term, which is the integrated, and we have seen this word actually in the integrated circuit. So in microelectronics component, we have a component called integrated circuit, IC, right? So this integrated word is actually coming from the integrated circuit term, because it's analogous to the functionalities of the integrated circuit in the microelectronics. And this is actually the following the trend of coaxial copper cable over fiber optic. So basically what we have here is actually microelectronic industry. Now they use electric current, right? So all the processing, computing, switching, they do based on the current flowing or not. All right, so that's the basic concept of transistor inside the integrated circuit. And nowadays integrated photonics provide alternative for that. So instead of pump in current in your chip, in your integrated circuit, you can pump in light into your integrated circuit, so that you can have in the end photonics integrated circuit. So this is actually following the trend of coaxial copper cable. Before, we use coaxial copper cable for internet, for example, for long range data telecommunication, for internet and so on, we use copper cable. But we know by using copper, by using electric signal, we have high loss. All right, we have high loss. It is not entirely it's subjective towards interference and so on. There's many disadvantage of using copper cable. That's why we switch for fiber optics. All right, so we switch from the electric, from flowing from carrying our information into electric signal to a light signal, okay, that we have achieved using our fiber optics. So this is just few of the example of integrated photonics component or device that consists of actually different parts that we will discuss in greater detail after this. All right, so the demand for transition from electronics to photonics is due to two reasons. The first is due to the data telecommunication demand. In 20th century, we saw transition from the isolated data process to distributed processing, which referring to internet. So before, in 1960, for example, without when there's no internet, when you have a computer, you can only access whatever we have in the computer, right? Whatever we have stored in the computer, we can only access that file. But by using internet, we can save our file somewhere else, not necessarily to be in our computer, right? So in this internet world, we need to have huge amount of data to be transferred in a very fast rate, especially the session that we have now is actually using the same principle, right? So you are viewing the lecture now from your computer, but the data of the video is not necessarily safe, not actually safe in your PC. It actually is taken from a data center somewhere. All right. So it requires a lot of data to be transferred in a very fast rate. And this caused the migration from coaxial copper cable to optical fiber was inevitable. We need to change into fiber optics. And optical fiber technology enabled recourse, distribution, and performance enhancement. As I mentioned just now, the light confinement fiber optics is very, very high in terms of the transmission. So we can confine light in the fiber optics that have the length hundreds of kilometers with a minimal loss. All right, and also very, very cheap in terms of the cost. And photonics technology evolved to meet the growing bandwidth requirement. Like I mentioned just now, the bandwidth requirement keep increasing. Especially now we use internet almost for everything. All right, so even for autonomous car without driverless car, we use all the data from internet to navigate and so on. So this is actually very important. This is actually the trend. The bandwidth that we require will be increased exponentially. All right, so from the bandwidth can increase from tens to hundreds of gigabytes per second by using fiber optics. And advanced wireless communication is not fully supported by optical fiber technology, for example 4G, 5G, and beyond. Okay, so for wireless communication, we might not the fiber optic technology might not be compatible anymore. We need to have a new technology for that. And the second demand for the transition from electronics to photonics is in terms of computation. We know the processor in our computer is actually consists of billions of transistors. Right, each of the transistors actually doing the switching 1 and 0, creating the binary number. Okay, for example, when you press into one of the key in your keyboard, okay, one letter, for example, A, you actually registering 8 of the 101010. Okay, so that can how we store information. So to store more information in our processor, or to process more information, we need to have more transistors that do the switching. All right, so to have more transistor in the same chip, what we can do is we need to scale down the size of each of the transistor. For example, from the big transistor, we need to divide into 2 so that it become a smaller transistor for data processing and also data storage. Okay, and in terms of the functionality and speed also, it depends on how many transistors that you have in the chip. All right, so that's what has been predicted by Moore's law. Okay, Moore's law is actually one of the engineers in IBM, I believe, and it has been 120 years ago, this prediction, and this prediction actually holds true, which is the number of transistors inside a single chip will be doubled in every 2 years. In every 2 years, for example, this for we can see here 1920. All right, so we have this amount of transistor inside the chip, and 2 years after that, 1922, 2 years after that, we have doubled the number of transistors in the same area, in the same size of the processor. So this is what given what has been predicted by Moore by using his Moore's law. All right, but lately we see the slight deviation from the linear trend that we see for Moore's law. This actually comes from or originates from the limitation of the copper. So copper interconnects that connects between various processor that become the bottleneck for the increasing the speed of the processing that can be done. All right, so and if you can imagine in the processor, in a single processor, okay, so to achieve more functionality and to achieve more bandwidth, what we need to do is we need to divide our transistor into half, all right, so that we can have more transistor. But there's actually a limit to it. When the transistors start to be in the nanometer scale, so the transistor will be very near with one another, and what we will have is actually the ESD effect. So electrostatic discharge, whereby the current from the one transistor will jump into the neighboring transistor. In that case, we cannot have the switching, right? We don't have the switching anymore. So that's the issue with the copper, and that is actually where photonics can provide a solution. We can use light to do the computing. Okay, so just now I talked about bit 1 and 0. 1 means current is flowing, 0 means current doesn't flow, right? So we can achieve the same computation by using light. In this time we have 1 represent current, the light flowing, and 0 represent the light not flowing. There might be different techniques to do that, but this is one of the switching technique can be done by using light. All right. So let's look at the electronics integrated circuit, or in short, we just call it an IC. All right. IC is actually integration of components to provide miniaturization. I have discussed this before. So before, our circuits, our electronic circuits is big because each of the individual component, for example, resistor, diodes, capacitor, is big in size, right? So in the end, we'll end up with a big device system, and to miniaturize the system, we need to build everything on the same chip, on the same platform. So this is what we have achieved by using integrated circuit, which is we have achieved bulk process on a flat thin substrate or chip. Okay, so in that chip, we can have different process functionalities and also processes that can be done by the chip. And once you made something into a chip, the cost will definitely reduce. All right, so because now you only require very small or very less raw material to begin with. So the size of a single chip now, instead of it can fit in your palm of your hand, now it can just maybe just a few millimeter. All right, so the device has been reduced in the form of factor, in the size and form factor, so therefore we can reduce the cost. So another definition of integrated circuit is individual component put together in a desired fashion to achieve a desired functionality. And this is what can be explained by electronics integrated circuit. Discrete component, individual circuit blocks resulting in a global functional circuit. So you need to have a circuit that have specific function that we want to have, that we plan to have in that circuit, and these can be achieved by using a photonics. So instead of electronic integrated circuit, now we can have photonics integrated circuit. So the functionality, the concept, everything is the same. Just the difference is, instead of pumping current in your chip, now you pump light into your IC. So integrated photonics in overall or in general can refer to fabrication and several photonics components on a common planar substrate, okay, in a single substrate or in a single platform. We build everything, all the optics component on the single platform. And integrated photonics constitute by combining guided wave technology with other disciplines in optics, such as electro-optics, nonlinear optics, optoelectronics, and also magneto-optics. All right. So I give you example here. The one in the left is actually a bulk optical system. So the beam actually, the beam system is actually a free space optics, and the size of the system can be 1 meter length, all right, or 2 meter length. This can be done on the optical table. But by using integrated photonics, we can convert this into a very small chip, all right, that have the same functionalities. But now, rather than we do it in free space optics, we do it on the planar substrate in a single platform. And to do this, we need to play around with the material properties. All right, the material that we want the light to guide through, we need to study its electro-optics properties. We need to study its thermo-optics, magneto-optics, acousto-optics, and we need to check whether it has a nonlinear optics or it can be used as the optoelectronics. So these are the different parts of or discipline in optics which really enable the integrated photonics devices. In terms of the optical system evolution, we can divide the optical system into 3 generations. The first generation is conventional technology, where in our optics setup, okay, optical system, we have big component, bulk component, such as mirrors. We have prism to diffract the light. We have lenses. We have aperture. We have detector. We have separate laser, and so on. This is all the component that can be considered as a first generation optics system. And in this kind of system, the alignment was very, very necessary. If we didn't take care of the alignment, the beam will not be in the position that we want. So therefore, we need to play around with the mirrors, with the lenses, and so on. And the mode of propagation is on the free space beam. And the device size can be in a meter squared area. All right. So the typical size of optical table is maybe 1 meter by ½ meter. Right. This is actually this is definitely will be a big system. This is based on the first generation of the optical system. And the second generation is we call it a micro optics technology. So now every component that I mentioned just now, we can reduce its size into a micro component. So now we can start to use LED. LED can be very, very small. The LED itself is actually in a micron size, right? It's 1 micron by 1 micron size. But also, but the packaging, everything will make it like the size of the LED that we can have now. But the LED itself, the part of the LED that emits the light is very, very small. So is micro size. So we can integrate this in different components, laser diodes. We can have a micro lens, and we can also have optical fiber in the micro optics technology. All right. So the alignment is still necessary in this kind of application because we have different component. All right. We have different component, and we want to integrate all the components in the same platform or in the one system. So therefore, we need to do little bit of the alignment. In terms of propagation, we can use fiber optics, and also we can also use a free space optics for that purpose. The device size now has reduced into centimeters squared. We can have a device, much smaller device compared to the first generation. And the third generation, which is the next generation, is the integrated photonics, the field that we're discussing now. So integrated photonics enable us to build all the components, the optically active components or the passive component on the same chip, on the same platform. All right, we can have a single mode channel waveguide. We can have a laser diode integrate in the same chip. We can have LED in the same similar chip. All right. Just now we have separate in the second generation, we have separate LED laser diode. That means we have the laser diode, we integrate into a system. But in this third generation, we build everything in the same planar surface or planar substrate. platform. So in this case, we don't need alignment anymore because it's all on the same chip. You can imagine as building everything in a very small table, right? In the optical table, we can build everything on top of the optical table, but our optical table now is in micrometer scale. So the alignment was no longer necessarily. And the propagation, we need to use waveguide for that purpose. For the propagation in the integrated photonics, we need to use waveguide. And the device size, overall device size will be in a millimeter squared range. So this is a little bit more history of integrated photonics. It's actually not a new field, but I believe it has been like the word is rebirth. The field grows, and then like no one studied that, and suddenly the field start to grow, become more popular nowadays. Okay, in 1960, the scientists they study on the planar waveguide. So planar waveguide is actually a thin film, okay, thin film made of a dielectric material, and we want to have the light to propagate along the plane of the waveguide, of the planar waveguide. Okay, let me try to draw here if possible. All right. All right, so basically it is like a can I turn off my video because I need to draw on my laptop, and to do so I need to flip my laptop. Okay, I'll turn off my video now. All right. Okay, so planar waveguide is actually made of different thin films. Okay, so we have N1 here, N2 and N3, which can be made of different material, right? With different refractive index. And what we want to achieve is waveguiding along the planar waveguide. This is what we call a planar waveguide. All right. So what we have here is actually 1D confinement of the optical field in a very thin layer of material. So this is a planar waveguide. And in 1970, the researchers start to work on the 3D waveguide. Now, instead of 1D confinement, the scientists study about the 2D confinement of light in a waveguide. So in the end, we have this. We can be made as two materials. All right, it's difficult for me to draw. I hope you can imagine that. All right, so our waveguide now is actually this rectangular on top of the thin layer. So now we have achieved 2D confinement. That means the light will only pass through, will propagate along this this is rectangular structure on top of this thin film. Okay, in 1980s, the material that was very popular is the lithium niobate. Okay, that has been used in the form of waveguide that enable the first on-chip optics by using this lithium niobate. It has the electro-optics properties. In 1990, the integrated photonics start to involve 3-5 semiconductor material, because 3-5 semiconductor materials such as gallium arsenide, gallium nitride, indium phosphide, and so on, they are direct bandgap semiconductor, and because of that, they can produce light in very efficient manner. All right, because of the 3-5, because of the direct bandgap. And also in that similar time, we have the birth of silicon integrated optics. This is actually a continuation from the silicon technology that we use in the microelectronics industry. So in the microelectronic industry, we have CMOS technology, right? We fabricate our device on top of silicon, by using silicon. So in 1990, they start to use the same technology for the integrated optics or integrated photonics. And in the 2000, 35 integrated photonics device are already in the market because they are easy to work with because of the direct band gap and so on. But CMOS based or silicon based photonics having some difficulties to penetrate the market because of the rising issue. The first is the huge loss in the silicon waveguide. Okay, even though silicon is transparent in the telecom wavelength, but we have a huge loss in the silicon waveguide, which cannot be explained by the scientists that time. So they don't know why this happened. And over the time, the field of silicon photonics evolved once the researchers have found the answer to that. All right. So basically the issue is because of the surface scattering, because of the high confinement, we confine light into very small space, 3D space along the rectangle waveguide that I showed you just now. All right. So because of that, we have the scattering effect, and the scattering effect is actually dependent on the refractive index mismatch between the waveguide and also the surrounding. And secondly is because the huge, because of the huge refractive index contrast between the core and cladding. This is what I mentioned just now. And the third is due to the contamination issue. So in the silicon system, waveguide system, if you got one carbon atom on top of it, we have absorption, right? We know carbon can absorb light, can cause absorption, and this absorption is not small. Is going to contribute to very huge contamination loss issue in the silicon waveguide. So that's the issue with the silicon photonics. But in that time, 35 semiconductor material are okay. All right. In 2010, silicon photonics source and detector integration, germanium on silicon platform as a detector and light emitter has been achieved. And so basically heterogeneous integration of 35 semiconductor on silicon. So silicon is actually an indirect bandgap semiconductor. Silicon cannot produce light. So it's very inefficient way to produce light by using silicon. So therefore, we need to introduce different material on our silicon system. So this is where the germanium silicon material comes. We have the integration of 35 semiconductor and so on. And recently, last year actually, according to the milestone, the silicon photonics is already in the market. All right. If you check, if you compare with the 35 semiconductor platform of photonics integrated circuit, it has reached the market in 2000. But silicon photonics it has been given a new life, if I can say, if I may say. All right, this is what we have discussed just now. I make summarize of it. So there are different platforms of the integrated photonics. By platform, we means the substrate that we build our optics component on top of it. Remember, we want to achieve optical system on a chip. So that chip must be made of a substrate, and this is what the substrate is based on. The first is based on the silicon or silicon-based material. This is actually the 90% of the integrated photonics devices are based on the silicon, because we leverage on the 50 years of maturity of silicon foundries to make CMOS. Right? We have become very good at manipulating the structure and the size of silicon structure. Silicon structure on top of silicon, so we can use that as to build our integrated photonics, to build our mirrors, to build the waveguide, to build the other components that we can have in the silicon. But silicon is not alone. Actually, silicon can be used together with silicon nitride, silicon carbide, silicon oxynitride. We can also use germanium, because all material has already been used in CMOS foundries. Okay, to produce CMOS that has been used in your cameras, the sensor in your camera and so on. This is we can use the same technology to produce the camera, the camera sensing unit in the camera, right? The sensor area to build our integrated photonics. So this is actually a way forward. So we can use all the equipment that we have in the silicon foundries to do the integrated photonics. And we also we can have the 3-5 semiconductor platform based on gallium arsenide, gallium nitride, indium phosphide, and so on. And also we can have a ternary alloy semiconductor, indium gallium nitride, and so on. All right. And the next platform is actually planar low index material. It can be made on the titania, alumina, and also polymer. So example that I gave you here is organic thin film photonics integrated circuit. So the system is actually on a thin film made from polymer that is flexible. So you can imagine a lot of application can be done by using this. We can put a sensor on top of our skin, for example, and so on. All right. Okay, so when we say about integrated photonics, integrated photonics, you might recognize silicon photonics more than integrated photonics or optics, because silicon photonics is become more popular nowadays because the reason of that I mentioned just now. And when we see the market forecast of silicon photonic transceivers, we can see a tremendous increase in the market forecast, in the market size. And there are a lot of challenges in the silicon photonics, and it is actually being solved as we speak now. Actually, this is not an old problem. This is actually current problem. We have issue with the high speed that I show here. All right, so we have a lot of issue. For example, the recent one in 2020, we want to integrate quantum dot laser on top of a silicon. This is yet to be optimized. I believe it has been observed, but it's yet to be optimized. And 2021, this year, we expect to integrate more material on silicon germanium. We can put graphene on top of the silicon, organic, polymer, 3-5 semiconductor, and so on. All right, so these are the challenges, and also the predicted technical breakthrough which year that it can be solved. In terms of application, silicon photonics, there are a lot of application of silicon photonics or integrated photonics in general. We can use them as a data centers to replace our integrated circuit. All right. So in data centers, we want to send a lot of signal, huge size of signal, huge amount of signal or information in a very fast rate. So we can achieve that by using light. All right. And we can use also silicon photonics for high performance computing, for optical computing or quantum computing applications. And we can use this as a telecommunication application, aeronautics, aerospace. We can use them as a sensor. We can use to build a medical devices and autonomous car. So this the autonomous car is actually one of the interesting application of silicon photonics that we want to that we can use silicon photonics to tackle the issue of the LiDAR. The LiDAR issue that we have now is the LiDAR system is very big and expensive. So to have our LiDAR system cheap, we need to build the LiDAR system on a chip, right? And to do that, we need the silicon photonics. We will talk about the application in the last part of our lecture. Let me check the time. We still have 1 hour. Okay. This is the features of integrated photonics. It is based on electromagnetic optics. Based on the Maxwell equation, we can explain the propagation of wave inside our waveguide by using the Maxwell equation. And it has stable alignment. That means we don't need alignment. Alignment is not necessary. And we can have a control on the guided modes that we want in our waveguide. Because now it is very small system, we can have low voltage control. We don't need huge power of light. We can have high speed operation by using light. We can have more effective light matter interaction. If you want to probe into matter, we need to have our light interact with that material. So to achieve that, we can confine light in our waveguide, and by doing so, we can have effective light matter interaction. And we can have high optical power density in a chip, in the waveguide, and the circuit will be very compact. And because of the very compact, we can produce the chip in a high scale or high volume. And we can have the all right, so we can also have build different chip, and we can integrate them together to become a device. So this is the component in Photonics integrated circuit, PIC. In a PIC, Photonics integrated circuit, we should have a light source. This is where our light will come from, and we need to have a light coupling. We need to have how we want to couple the light that has been emitted by our laser into the waveguide. And next we have a guide light or waveguide. This is like our fiber optics, but instead of inside the cylindrical fiber optic that we have, we can guide light on top of our substrate. And we can have a wavelength filter. We can have we can modulate the light by using very many properties: electro-optics, acousto-optics, magneto-optics, and so on. And we can also create or build our photodetector on top of the single chip. All right, so all these components can be integrated to have a specific functionalities inside a single chip. So that's the aim of Photonics integrated circuit. And we can divide these components into two. The first is passive, and secondly is the active. Passive component means components that depends on the intrinsic properties of that structure or that component. For example, waveguide, we cannot change the propagation of the waveguide unless we change the waveguide, right? That's the passive. We cannot change the characteristic of the single waveguide. But for active component, we can play around with external field or external factor to change the properties of the light that we have in our chip. So in the passive, we can have waveguide, we have couplers, we can have switches, optical interconnect, we can have wavelength selective switches, we can have filters, mux, demux, demultiplier, multiplier. We can have dispersion, compensator, attenuator, gain, equalizer, isolator, and circulators. That's for passive. For active, we can have amplifiers. We can amplify the light. We can have laser is one of the active component, LED, modulators, detectors, wavelength converters, and so on. So we can easily divide the component into these two categories. But it's not just limited to this. This is not a comprehensive list of the component. We can have beam splitter, we can have grating, couplers. We can also have mirrors like we have in our free space optics. Now we can build mirrors on top of our chip. We can have also polarizers and also interferometer. Okay, so we discussed about Photonics integrated circuit. So why we have the word circuit there? Circuit, we use this in the race track. Okay, this is a race circuit. So the word circuit is used because we have a specific reason why we have this shape of the road. For example, for this one, we want the car to be fast, and then we have a corner here. We have a corner here because we want the car to slow down. So that is the same with our waveguide. the way we build our waveguide is because of the specific functionalities that we want to have in our chip. All right. So how do we guide light? Okay, the first way is by using reflection. This is what we can have in our free space optics. To have our light travel from point A to point B, we can use mirrors. Right? We can use multiple mirrors so that the light can be reflected multiple times before it will end up in point B. So that's the first way. The second way is by using refraction. Okay, so now instead of using mirrors, we use lens. So we use lens to guide the light from A to point B. So that's the second way how to guide light. The third way is by using total internal reflection. Okay, so this is a waveguide, a material. So to guide the light from A to point B, we place a material in between them, and under specific condition, all right, we can have total internal reflection, whereby the light will be reflected at the interface between the material and the air. All right, so in the end, we will have the same effect that we have for mirrors just now. All right, so this effect is called total internal reflection. I'm sure you have heard about it, and this is actually the basic operation of the optical waveguide. Okay, which is the light confinement through total internal reflection. And if you see the basic of this is based on Snell's law, and it's very dependent on the intensity of the material and its surrounding. All right, so for example, in the waveguide, in the optical fiber is one type of a waveguide. All right, optical fiber is one type of waveguide that use the same mechanism, which is total internal reflection. All right, so in our optical fiber, we have core and we have cladding. So to guide the light through the core, the N, which is the refractive index of the core, need to be higher than the cladding. All right, so that's the basic concept or basic operation of the waveguide. And by using waveguide, we can achieve low loss light propagation. And I mean by using waveguide structure, we can have low loss light propagation, and therefore it has been used to connect components and also devices. And waveguide is actually the building block of optical device or circuit. Optical waveguide is the building block of any optical device or circuit. All right. But to understand the total internal reflection or the guiding of light inside the waveguide, right? We need to use the concept of our scalar wave optics just now. Remember, we have 4 theories related to light to explain light. We have ray optics, we have scalar wave optics, we have EM wave, we can also have quantum optics. So we need to discuss this, or we need to view this from the scalar wave theory. All right. So in scalar wave theory, the propagation of light can be represented as a wavefront. All right, this is a wavefront. So if you can imagine here, this is the propagation of the light, and this is the wavefront of the light. All right, wavefront of the light. So if you can imagine, this will be the wavelength of the light. That will be the distance between the two successive wavefront is the wavelength, right? Okay. And for this light that has been reflected just now, this is the red line will be the wavefront of this second of the reflected beam. So therefore, what we have here is actually overlapping between the wavefront. So we learn from the wave properties, when the wave overlap with one another, we will going to have interference, right? So we're going to end up with whether in constructive interference or destructive interference. So to have our light properly guided into the waveguide, we need to take care of this issue, which is the interference that occur in our waveguide. Okay. Okay, so basic concept of waveguide, I mentioned just now, the refractive index of the core, the N, must be higher than the cladding. So there are two types of waveguide in terms of the structure. We have a planar, or we call it slab or thin film waveguide. Okay, so this is what I have drawn just now, but it's not, maybe you cannot have the clear picture of it. So this is our planar waveguide. So we have 1D confinement here. So the light is only confined within one dimension. All right, if we name it as a Z, so the light is only confined in one dimension according to the thickness of the core. Okay, so because of the 1D confinement, we will have higher loss due to this shape. And the typical length for this structure is, for the wave to or the light to be guided in the planar waveguide is tens of micron to tens of millimeter. So it's very small. So the light will be guided along this length, along this distance, tens micrometer or tens of several tens of millimeter. And because of this, we have 1D confinement, the waveguide is in a planar structure, we will have a pure transverse electric and also transverse magnetic mode. So pure TE is one direction, and TM mode. This we talk about actually about the polarization of the light. And because of the planar waveguide, we can have a whether pure TE or pure TM mode. And this structure, even though you have a higher loss, this is actually the key structure for semiconductor laser. We can use this structure for passive device such as a filter, wavelength filter. We can use it as a WDM, with wavelength division multiplexing. We can use this structure or this form factor as the active devices such as electro-optics, magneto-optics, and so on. On the other hand, we also have non-planar waveguide. Non-planar waveguide, as you can see from here, it is a 2D confinement. Okay, so basically our light will be confined in the 2 dimension. If we name it as a Z and X, all right, so it become a 2D confinement. The light is confined in both direction or dimension. All right, so we still have the same. The core is where the light, our light will be guided, and we have cladding in this outside of the core, right? Outside of the core, and the rule still applies, which is the N core refractive index of core should be higher than the refractive index of the cladding. So the non-planar waveguide, we have high light confinement. Okay, high light confinement. We have minimal loss. And we can use this for long-range application. For example, our fiber optics is one of the non-planar waveguide. We can use the light. We can propagate light inside the fiber optics in hundreds of kilometers. And because of now, our structure is no longer a plane structure; it's non-planar. So therefore, we will have a quasi TE or quasi-TM mode. It's no longer pure TE or pure TM modes, all right, because of the structure. And to predict whether our waveguide can propagate light or not, we can use a tool named Maxwell equation. We can use Maxwell equation to predict whether our light will propagate along our waveguide. This is type of waveguides based on the N variation, which is the refractive index variation. We can have step index waveguide. So this is the core and core. This will be the N cladding. This is another cladding. Okay, so we call it step index because we have abrupt change in the N, in the value of N. Abrupt change in the value of N between the cladding and the core. And we also have a graded index waveguide. Graded index means we have, this is still the core. This is cladding. Hopefully you can see the whatever I'm writing there. Okay, so now instead of abrupt change in the refractive index, we have a very slow variation of the refractive index. So this is what we call it graded index. So to achieve this, we can do a lot of material manipulation in terms of the fabrication technique. We can we can dope the material with different material in different concentration, so that we'll have different profile, or we have that profile of the refractive index. And we can also have a hybrid index waveguide, whereby we have abrupt change of the refractive index between the end cladding and also the core. But in the core itself, we will have a graded index. So in this type of waveguide, we call it hybrid index. We have because we have a step index, we also have a graded index in the profile of the refractive index. Just now I mentioned about two types of waveguide. First is planar and second is non-planar. Non-planar waveguide is also called channel waveguide. It also called channel waveguide, and there are a lot of configuration, a lot of types in terms of the structure of this kind of waveguide. It can be a buried waveguide. Okay, buried waveguide. This is our core. All right, this is our core, and this will be our cladding, the outside one. This is called buried waveguide because the core is buried inside the cladding. All right, the core doesn't have interface between with the surrounding, so that's the buried waveguide. Second, we have diffuse waveguide. This is our substrate. Sorry about that. This is our substrate, and instead of a rectangle, we have this kind of hemispheric or half cylindric structure of waveguide that we diffuse along the surface of the, that has been diffused along the surface of the substrate. So therefore, this is called a diffuse waveguide. If you can see here, we don't have any change in the thickness of the waveguide because the waveguide is actually inside, consume the thickness of the substrate. Next is we have a ridge or wire waveguide. Okay, this can be considered as a wire, a rectangular wire. Actually we have a substrate and we grow core. We do some fabrication to have this structure. This is the core. This is the core on top of the substrate, right? Okay, so in this case, our cladding, we have two cladding for this case and this case. So the first cladding is here, and our air will become the second cladding. Excuse me. Okay, so same goes here. We have N cladding 1. This, the air will become the second cladding. And beside that, we have strip loaded waveguide. If you can see the difference between the ridge or wire waveguide with strip loaded is we have 3 layers now, 3 types of material. This is the core. The black one will be our core. This is our cladding number 1. This will be our cladding number 2. So core, let me write it. Clad 1, clad 2. All right, we have the 2 claddings also. Okay, so in this case, the light will be propagated at the interface between the core and the cladding here. So this is special for strip loaded waveguide. We can also have arrow waveguide. All right, this is a unique type of waveguide, arrow waveguide, that consists of 3 layers also. All right, and we also have a rib waveguide. Okay, the difference between rib and ridge just now is we have this 2 layers, and the the core is actually just not made of this rectangle. Actually, it creates this shoulder shape. All right. If you can imagine, this is the head. This is the shoulder of the head. So it's made of the core, the same material as the core. Or also this type of waveguide is called rib waveguide. This is important for electro-optics application, whereby we need to probe, we need to introduce current into the waveguide. So the way we do that is we put a metal contact here and metal contact there, and now we can pump in current, electrical current in the waveguide. And next, we also have a slot waveguide. Okay, a waveguide is actually the same like a ridge or wire waveguide, but instead of one, we have two strip or two wire. But in this case, when we do the solution, when we solve this propagation of light along this slot waveguide by using Maxwell equation, we notice that the wave actually will propagate along the space in between the wire, right? So the different different optical or light confinement in a slot waveguide. Okay, so this different waveguide structure is different, is useful for different application. For example, for like I mentioned just now, rib waveguide is special or is suitable for the electro-optics modulation. And for slot waveguide, we can actually use this a lot for sensing. All right, because of our sensing, we actually want to sense the reflective index in the surrounding. All right, so in the slot waveguide, the light actually propagates in that region instead of the core. It propagates along the space between the core. All right, therefore we can maximize the interaction of the guided modes with the surrounding. Okay, there are three types of functionalities of waveguide. The first is power handling, polarization handling, and the last is active interaction, electro-optics, magneto-optics, or thermo-optics, and so on. Okay, let's discuss one by one. This time I need to turn off my video again. Sorry about that. By the way, are you following me? You can hear my. Are you following?
Yes, sir.
Yes, sir. Thank you very much. All right, so now we talk about the waveguide that have the function as a power handling. Okay, so what we want to have in this type of waveguide is we want to transfer the power of the light from A. For example, this is point A, this is point B. So we want the light to transfer from A to B. How we do that on a chip is we can have a straight waveguide. All right, we can just take any of the structure of waveguide that we have just now, and once we have the criteria for total internal reflection, we have the guided modes. So therefore, we can have the light traveling or propagating along the straight waveguide. Or if we want to move not in straight line, we need to make it into S-band. All right, S-band, a little bit corner here and there. So in the end, we can have from A to B. So the optical power from A will arrive in the B position with a minimal loss by using waveguide. This is actually the same concept of fiber optics. All right, so we don't want to make it to make the band too extreme so that it will induce loss. Right, in the fiber optics, we don't want to bend the fiber optics too much, because we don't want the total internal reflection criteria to be to not occurring. All right, so we want the total internal reflection to occur, so we need to limit the band that we have in our fiber optics. Same goes with here, but instead of flexible, this will be a fixed waveguide. So once you have made the waveguide into S shape, you cannot change the shape, right? That's the passive. That's what we call it, passive component. And we can do also a power splitter 1 to 2. So to split power, or to split a beam, sorry about that. To split a beam in a free space optics, in a free space of optics, we can have light. Oops. All right. In a free space optic, if you want to split the light into two, we can use a component that we call it as a beam splitter. All right. So this is the incoming light, and the light will be reflected that side, and the transmitted light will go that direction. So that's easy for free space optics. We can use a beam splitter, and we can design the beam splitter that works as a 10-90, 50-50, and so on. All right, depending on the how we design our beam splitter. And to do that, to do the same process on the chip, we can have two ways. The first is by using Y branch, this one. Okay, so we make our waveguide into Y shape. All right, so if let's say we have 100% here, we can design in such a way that it can be 10% here, 90% here. All right, we can split the beam how we want. So that's one way. The second way is by using a component called multi-mode interference. Okay, multi-mode interference. So in multi-mode interference, we have our waveguide. This is where our light input comes in. And we have a planar waveguide. This is a planar waveguide. And we have two outputs. Remember, we have planar and we have non-planar. So this should be non-planar. This one should be non-planar, and this one is planar waveguide. All right. Like I mentioned just now, the light propagating inside the waveguide, we need to consider the electromagnetic wave theory given by Maxwell equation. So if we have a waveguide, the planar waveguide like this, we only have a few characteristic solution of the wave of the light. All right. Example, we have like this. This is incoming light, and in this by designing our planar waveguide just now in such way that the light that can exist in the planar waveguide will interfere with one another, and the end profile that we can have at the end of this planar waveguide looks like this. Not really nice. Let me draw again. They will have. All right. So remember the interference phenomena. We have destructive and constructive interference, right? So by placing a planar waveguide in between this non-planar waveguide, we have interference between the light that comes in, and that the result of that interference is we're going to have a peak, right? Two peaks that coincide with the output of our MMI, multi-mode interference component. So the most important thing for this this device is we need to play around with the end of this planar waveguide, and we need to also consider the length of it. All right, because we don't want loss. We want the light to be guided into the for example, this one is A, this one B, this one C. Right. So in the end, we want the constructive interference peak will be guided through B, and the interference here, constructive interference here, will guide it into C. So in the end, we're going to have the same effect as before, all right, which is the beam splitting effect. And we can design such that it can be a 50-50. Usually it is a 50-50 for multi-mode interference. All right. That's for power splitter, and we can make it into 1 times 4, right? So what we do is we put this into another splitter, Y branch, this one also. Let me try to draw it. Okay, it's not very natural position for me to draw, therefore it's not very nice. My drawing is not so nice. All right. Hopefully you can imagine that. Okay, so we put another 1/2 Y branch power splitter. So in the end we can have, for example, we have here is 50-50, and here in the end we will end up with 25, 25, 25, 25%. Right? So instead of 1/2, we can have 1/4 power splitter. That is for power splitter to handle the power. Next, we have a waveguide reflector. So in a free space optics, if you want to reflect the light, we need to use a component called mirror, right? We put a mirror, and our incoming light, the light that we want to reflect, the light will be reflected at the mirror. We can do the same in our chip, all right, in our waveguide. So we place a mirror perpendicular to the cross section or the parallel to the cross section of the waveguide. So by doing that, we have a reflection because of the mirror. And we also can do the reflector by using grating, right? Okay, grating. So imagine this is our waveguide, and we create a variation, multi-layer of thin film, not thin film, multi-layer of different alternating refractive index. For example, this one N1, this one N2, N1, N2, and so on. All right. So actually, we create more interface or many interface between N1 and N2 in the waveguide. Right. So based on the optics theory, we know when we have a mismatch between the refractive index, this case is between N2 and N1, N2 and N1, we know part of the light will be reflected, right? So in this, in here we have the mismatch between N1 and N2. What we're going to end up with is reflected light on that surface. Here also we have another reflected light. So in the end, we have many propagating or reflected beams. Okay, so the effect of this is actually all this reflected beam will be interfered with one another, and in the end we're going to have a beam reflected back from our waveguide. So this is our grating just now. It consists of alternating refractive index material, N1 and N2, and like I mentioned just now, we have reflection occurring in all of the interface between N1 and N2, and all those light reflected just now will going to interfere with one another and create a reflected beam, which is opposite to the direction of the initial propagation of the light. So that's another way of having a reflector on our waveguide. We can also have a coupler. If you are used with the fiber optic coupler, this is also almost the same concept. All right. So we have two inputs and we have two outputs now, directional coupler. Okay. So what we actually have in this coupling region is actually we try to move or make the two waveguide very close to one another. So if the waveguide is close to one another, we have a coupling, right? We have a coupling from one waveguide to another one. And by designing different length of the coupling, distance between the waveguide, by designing the structure, basically, we can have this directional coupler. For example, I give this as a A, this as B, C, D. Okay, by using directional coupler, by engineering the coupling region, we can have the light from A to go to D, all right, or the A to C, B to C, or B to D, right? But this is, of course, is a passive component, so therefore is a directional coupler can do only one process. For example, A to C or A to D. That's about the few example of power handling waveguide. And second is polarization handling. Polarization handling. To do the polarization handling in free space optics, we need to use a polarizer. We need to use a polarizer for input that have the TE and TM modes. All right, we put the polarizer, and the output of the waveguide will be a TE, only one direction of the or polarization direction. Okay, so to do that, we can, for example, this is our waveguide. This is our waveguide. This we have TE and also TM. We have two polarization of the incoming light. Right, what we want to have is we want to polarize the light, whether it's only for TE. So in the end, we have TE, transverse electric mode, or TM, just one, TE or TM. So to do that, okay, so to do that, let me draw this first. This should be our E, H. H is magnetic field, E is the electric field. This can be regarded as a TE. If this is TE, we can have another one. This one is H, this one is E. This is TM. Sorry about that. Okay. So this is the polarization of TM, on this is the TE. So light propagating along our waveguide will have specific loss in the TE and TM direction. All right, they have specific TE and TM. So in our case here, we want to have maximum loss for TM mode so that we will end up with the TE only. Right? We want to have maximum loss for TM. So to do that, we place a thin layer of metal on top of it. This can be metal. All right, metal is, we know it has very high refractive index, and by placing this metal, this TM wave, TM modes will be coupled into the metal because of the high refractive index of the metal. So in the end, we can increase the loss of TM only. All right. So we can do some engineering in the structure. So in the end, we going to end up with only TE or single polarization beam. That is as a polarizer, and we can use waveguide to do the polarization beam splitter, but this time we need to use anisotropic substrate. So anisotropic substrate is a substrate that have two refractive index. Right, it has two refractive index or birefringence. So if you go one direction, it has different refractive index. We go another direction, it will have different refractive index. So we can use that material to split from our TE and TM modes into an individual TM and one channel or one waveguide for TE only light. All right, that is with polarization beam splitter by using waveguide. And we can also have a TE or TM converter. For example, we already have TE, transverse mode, E mode, and we want to change it into TM mode. So we can do that by using this TE TM converter. And the easiest way to do this is by using electro-optics modulation. We supply current into the crystal, for example, lithium niobate, and in the end, we're going to change the polarization of the light, of the incoming light. From TE, we end up with the TM, or from TM, we will end up with the TE. Because some application, we need to have the light polarized in certain direction, right? We don't want the light to be randomly polarized, right? So basically, polarization means the direction in which the electric field in the light propagates. That's about the polarization handling. And the next functionalities or function of the waveguide is as an active interaction, whether it's electro-optics, magneto-optics, or thermo-optics. The first, we talk about phase modulator. All right. So we have light input that looks like this. This is the oscillation of the electric field. And what we want to achieve is we want the light to be slightly shifted in terms of its phase. All right, this one. So how we can have the phase shift is by changing the refractive index of this material. All right, change the refractive index in this material. In this case, this will be the part that we're going to have change the refractive index. And the way we change the refractive index, for example, this one is silicon waveguide. All right, we want to change the silicon, this part of the silicon waveguide, we want to slightly change the end. So to do that, we pump in current into that region. All right, so we have two electrodes. So by pumping current, we going to increase the charge carrier concentration in that part of silicon. So in the end will change. All right, the end will change, the phase will change. All right, talking about phase changing is very important in interferometer. All right, in interferometer, we have a reference arm. Let me draw like this. We have reference arm. We have this will be the arm that we change the phase. All right, this one should be our detector. This will be the light. This is the beam splitter. All right, so we have two arms here. This is reference arm. This is the arm that we change its phase. All right, we change its phase. So we can use the phase modulator just now as an interferometer. All right, we can use it as an interferometer. So in the end, we will end up with this Mach-Zehnder interferometer. And this is active interaction because now we can control how much we want the change in N happens, or in this case, how much the phase we want the phase to change, because interferometer is very sensitive towards the change in the phase. So that's how we by the way, this interferometer can be used as an intensity modulator. We know interferometer will produce the constructive interference and destructive interference. All right, if you can recall from your experiment from before, we have dark spot and bright spot. Dark spot is where we have destructive interference. Bright spot is where we have constructive interference. So we can play around with the intensity by using this modulation. And we can also achieve frequency shifter. We have light input at certain frequency, F0. And this time we, instead of electro optic, we do acousto-optic. All right, acousto-optic is acoustic. All right, so we place a surface acoustic wave transducer on top of the chip. So we end up with the changes in the propagation of the light comes in. So basically, if we have light pump in like this is our frequency input, and the output frequency, we will have a sideband like this. Not really nice, but I hope you can imagine that. All right. Okay, we have this frequency sideband. This is the F0 just now. All right. So this is active interaction of the waveguide. So our aim is we want to modulate the light. Whether we want to change the phase, we can change the intensity, we can change it, and in certain cases we can change the wavelength also by using the in terms of the waveguide structure. So we have 10 minutes left. Actually, I have more slides to cover, but quickly, the device that comes out from the integrated photonics is called photonics integrated circuit instead of the integrated circuit for microelectronics. Now we call it PIC, and we can have different types of integration. We can have monolithic integration. We can have hybrid integration. So basically, this depends on whether we have all the components on a single chip or we have integration from different component or external module.
Sorry, Dr. Mujir, maybe 5 minutes, then discussion until
All right.
5 o'clock in Indonesia.
All right.
Yeah.
I think I'm going straight to the application. Okay. So application of integrated photonics. I mentioned just now we have a lot of application of integrated photonics. Sorry. We can have the most interesting for me, the integration in the integrated photonics is in the field of autonomous vehicle for LiDAR system on chip, and also for sensor purposes. All right, so LiDAR on chip, we can use, nowadays the LiDAR is very huge and complex system. So we need to have a mechanical part so that we can change we can steer the beam into the position that we want. So, okay, so we can steer the beam to the area that we want, to the field of view that we want. So by using the integrated photonics, we can build this on a single chip. So from this big that you have seen, I think you have seen on the Google car, right? It's a big machine on top of the Google car that's called LiDAR. And that's a big machine. And there's opportunity to use the silicon photonics or integrated photonics to make it, to turn it into a single chip. Okay, I will talk about a little bit about sensing, because I'm sure biosensing in particular. There are two fundamental ways of optical sensing. The first is by refractive index. We can change the refractive index. So in the end, the characteristic of light output will change. And we can also sense by using the absorption of the gas molecule or liquid surrounding the waveguide. All right, so a lot of sensing application that has been reported by using waveguide technology, biosensing in particular. This one they use to detect the binding of analyte. All right, so they have this pair of these analyte and its conjugate molecule. So in the end, we can use this as a sensor on chip. All right, photonics sensor on chip to detect various application. And we can also use the sensor based on the gas or liquid sensing based on absorption. So basically, we have absorption due to the evanescent wave. Some of the wave, not all the wave will be coupled into the core, like I show here. Some of the modes will be in the surface of the waveguide. So this is called evanescent wave. And by doing in the structure of slot waveguide, we can have huge coupling in the region between the two waveguide. So in the end, we have maximum interaction between the light and also the surrounding. That also can be done. And this is what actually happening in silicon photonics. They nowadays to check the glucose monitoring, we need to take a sample of blood, right? We need to do some procedure to take the blood, and we can use this silicon photonics chip implanted on the skin, under the skin, to measure the glucose concentration. So this is can be achieved by using photonic circuits on the chip. All right, this is another application in a biophotonics. This is to detect this arteriosclerosis. I'm not sure how to spell it, but it's basically related to related to our heart. All right, so this is actually the vibration mini vibration sensor. We use LiDAR system just now that I mentioned. We have light and we detect the light reflected back, and based on the reflected back, we can detect the vibration that translate into the condition of our hard basically. So that's all from me. I believe in the last part, I just go through quickly. I haven't have time to really discuss about the application. But thank you for your attention. I'm looking for option to see the video back again. I'm not sure how. All right, thank you for your attention. Maybe we have a Q&A session.
Thank you, Dr. Munji. Oke, ada yang tanya? Please ask to Dr. Munji. In Indonesia boleh, in English boleh.
Yes, both boleh. Sorry about my voice changed just now because I need to drink some water. So.
Yeah, please.
All right. Any question from participant?
Asif, gimana? Atau yang lain? Pak Asnawi.
Excuse me, I want to ask.
Yes.
Thank you for the opportunity. I want to ask about how is the principle of integrated photonics works, like when change a logic 1 to 0 or 0 to 1, like in the electronic.
Oh, all right.
Electronic kit.
Electronic.
Yes.
Okay. So, like I mentioned, one of the main reason why we push for the photonics integrated circuit is because we want to achieve the computation by using the light, right? So the switching from 1 to 0, we have a lot of techniques. It actually can be done in the microring configuration. Okay, so microring resonator configuration. So we can modulate the light so that some of the light will pass through or some of the light will not pass through. So based on that, we can do switching. That's one of the example. But other types, maybe in terms of the light flowing or not, that can be achieved by changing the Fetty index of the waveguide so that some of the light will pass through here, some of the light will pass through another waveguide. So that's some of the application to do the switching. But I'm sure that there are more better way to do the switching, which I'm not familiar with. Just from what I know is it can be done by using the microring resonator, and because we can do the we can have two states in the microring resonator. All right, we can have two states, and that states can be used as the bit 1 and 0 just now. All right, that's my answer for that.
Yes, thank you, sir.
Okay.
Next. Hasif, do you hear? Hasif. Ada, Hasif. We have student from Yemen, Dr. Munji. Ada, Hasif.
Thank you, bro.
Oh ya, silakan.
Master Abdullah, when potential waveguide and photonic implementation for COVID-19 interesting. How application in fabrication in laboratory USM Malaysia.
All right. Okay. Thank you for the question. Very interesting and very actually demanding application that we really need now. Actually, we don't have photonics integrated on to sense or to detect the COVID-19, but we do something else with the semiconductor, which we call it in the HAMD, in the power device configuration, so that we can detect the COVID by the binding of the molecules. This is done by different group, but not by myself. But we can use the same techniques. The basic just now is actually the conjugation, the binding between the molecules and its conjugate, right? So we can attach them on our waveguide plane just now, all right, so that it become sensitive whenever that interaction happen. That just the mechanism of the detection. And how we want to do that is we need to do the functionalities. We need to do we need to do the specific functionalities on top of the photonics chip so that it can achieve that purpose. All right.
Okay, thank you.
Okay, thank you. Ada yang lain? Any question?
It's actually dia sama dengan fiber optic sensing. Most of them, the technique of the sensing is actually the same. But rather than in fiber, we do on
Fiber
chip.
optic.
Same mechanism and same application can be done. We do for fiber optics. We can transfer them on the photonics chip.
Okay.
Yang lain? Any question? Mazda? Gimana?
Sudah tadi, Bro.
Yang pertama tadi Mazda, Prof Yasin, yang bertanya.
Tidak tanya lagi.
Prof,
Yang lain?
Prof, boleh tanya lagi, Prof?
Iya, silakan.
Gini, Prof. Kami ingin menjalin kerjasama baik dengan USM. Mana Prof untuk bisa menjalin kerjasama ini, bagaimana UNESA sekarang sudah harus waktunya untuk berkolaborasi.
Iya.
In Malaysia, khususnya di bidang optoelektronik, Prof.
Iya.
Jika bisa, Prof, bisa berkenan memberikan nomor kontak Mr. Abdella. Sebagai studi awal kami nanti untuk bisa berkunjung ke sana jika COVID sudah selesai, untuk mengajak beberapa kolega bisa join riset USM.
Ya, bisa jalan-jalan Pak Asnawi sana.
Ya, betul.
Ke Langkawi.
Dekat Langkawi, dekat.
Ya, ini Dr. Munjin. Pak Asnawi ini from University State University Surabaya ya. In Surabaya ini ada 3 big public university, Erlangga, ITS, UNESA, Universiti Negeri Surabaya. Ini join dengan USM gimana?
Dari segi research insyaAllah boleh. But kami punya bidang actually is on more optoelectronics. Kita buat on semiconductor devices to macam LED, diode pemancar cahaya, kita ada buat detector. Dan sebagainya lah, itu main kita punya research. But we still have this fiber optic sensor. We do sometimes optic sensor and so on. Actually, if you want to check our research, you can check in our website. I know at USM.my. We are institute focusing more on research, so we don't have undergraduate program. We only have the research program and the postgraduate. Basically just research driven institute. All right.
Thank you, Mr.
I still remember Nur in Al-Quran cahaya light. I still remember a few years ago I visited to USM.
Oh, no.
Yeah, no lab.
But now it have evolved into institute.
Yeah.
Before it's lab, now become institute.
Oh, institute, yeah. Okay, very good. Okay, thank you, Dr. Munjin. Time is.
Right. Thank you for the invitation.
Yeah.
Sorry, Prof. Sorry. I want to ask again the last question.
Oh yeah.
I was interested in the leader. How does the leader work?
Yeah, leader
detect distance, or for example, or others. How does the principle work of leader?
To detect what?
Distance or whatever. Just asking the principle work.
Oh, all right. So LiDAR works based on we want to actually the LiDAR stand for light detection and ranging. if I'm not mistaken. So that's LiDAR, and it actually used to detect or to map the surrounding. All right, in our autonomous car that has been proceed with Tesla doing the autonomous car, and for the car to be driverless, we need to have a sensor of surrounding. So that to create the 3D map of surrounding, we need to use the LiDAR. The basic concept of LiDAR is we send light. It can be pulse, it can be continuous. All right, and then after the reflection, the light reflected with something, with the object, and need to be reflected back. So based on the time, or it can be also based on the variation of the light. All right, we can detect how far it is from our position. So if we move the laser beam just now into different location, we can create another pixel, another point intensity to represent that. So if we do in all direction, we can create the 3D mapping of the surrounding. So that is actually what the Google LiDAR system works.
Yes,
Okay.
yes, thank you.
Yes. Okay, thank you, Dr. Munjir, for your explanation and presentation, and very useful for us. Thank you. Next, we can join again, yeah, the next lecturer. Might be more interesting.
Lecture. All right.
Okay, we can arrange again. Might be
like Prof. Ratna just
yeah.
it's on surface
Yeah.
resonance.
Yes.
Okay, yes.
Can,
For
yeah.
Inshallah.
Dr. Mundir,
Yes.
For the biology area application, I think it's very okay.
Just now, actually, I'm planning to focus more on biophotonics, but we don't have time. So
okay. Yes. Okay. Yeah.
I focus more on the basic concept and definition and so on. So
Yeah. Okay.
Next time can be improved.
The name of the lecturer is the biophotonic and photonic medical photonic, but I think maybe you can explain more again about the application of the biology area. Maybe.
Yeah, inshallah.
Yes, thank you. Is the wonderful presentation, Dr. Mundir?
Yes.
See you again.
Gimana? Take picture? Boleh? Pernah ngambil gambar? Nggak bisa. Atau Mas Jul? Mas Jul bantu.
Mas Jul, saya soalnya di HP
ya.
ini.
Bisa di on kan semua kameranya.
Ya, kamera on ya.
Dulu.
Kamera on semuanya.
Di sini ada 2 slide untuk sesi yang pertama. Slide yang pertama bisa di on kan semua.
Bentar, Yul, saya buka masker dulu, Yul.
Ya, Bu Retno harus lepas masker kalau selfie.
Iya, Pak Nabi sehat.
Oke. Untuk sesi yang pertama, senyum 1, 2, 3. Oke. Untuk sesi yang kedua, satu, 2, 3. Sudah, Bro.
Thank you, Dr. Munjir.
Dr. Munjir.
Okay.
Thank you, Prof. Yasin.
See you next time.
Thank you.
Kasih semua. Salam sehat semua. Thank you.
Salam nasi biryani. Iya.
Oke, thank you.
Assalamualaikum warahmatullahi wabarakatuh.
Thank you semua.
Assalamualaikum.
Waalaikumsalam.
Assalamualaikum, makasih.